All right, let's dive in. Today we're going to talk about a mathematical revolution that did way more than just invent some new shapes. I mean, it completely shattered our entire understanding of space, of reality, and even truth itself.
And it all kicks off with this one simple question. A question that, breaks a fundamental rule that we all learned in school. For literally centuries, this question was considered completely absurd. But the fact that someone was finally willing to answer it, well, that's what sets our entire story in motion.
Okay, so to really get what a big deal this revolution was, we first have to understand the kingdom that it overthrew. You see, for over 2,000 years, one single book, Euclid's Elements, defined everything. I mean, the geometry in that book wasn't just seen as a theory of space, it was accepted as the one and only true description of reality.
And, why wouldn't it be, right? This system felt like absolute self-evident truth. Why? Because it just worked. It perfectly described the world we could see around us, the world we could measure and build things in. It was logical, it was consistent, and everything you did in your day-to-day life seemed to confirm it. But this seemingly perfect kingdom had a tiny, nagging flaw. A single assumption that, for some reason, just didn't feel quite as solid as all the others.
So, this rule was called the fifth postulate, or the parallel postulate. And it basically says this. If you have a straight line and a point that's not on that line, you can only draw one single other line through that point that will never, ever meet the first one. And that's it. It just felt kind of clunky, It wasn't as elegant as the other rules. So for centuries, mathematicians tried to prove it using the other axioms. They thought this has to follow from the other rules, but every single attempt failed.
So after centuries of failure, this string of failures led to a really radical thought. What if the problem wasn't the proof? What if the problem was the postulate itself? Instead of trying to prove it, what if you just threw it out? What if you just assumed something different? Like, what if you could draw multiple parallel lines through that one point? Or, and this is even crazier, what if you can draw any at all?
Well, in the 19th century, this stopped being just a thought experiment. A few really bold mathematicians decided to see what would happen if they actually did it, if they actually broke Euclid's most sacred rule.
So, let's meet the revolutionaries, Carl Friedrich Gauss, Nikolai Lobachevsky, and Janos Bolyai. And what's amazing is that in this remarkable historical coincidence, all three of them were working on this at almost the exact same time, but they were largely unaware of each other. They all dared to build entire, logically consistent geometries based on these new, supposedly impossible rules.
And this was a huge deal. It led to this profound philosophical shift. Suddenly, postulates weren't seen as these unshakable, self-evident truths about the real world anymore. Nope, they were just starting assumptions. And that meant geometry wasn't about discovering the one true reality. It was about constructing any number of consistent logical worlds from whatever set of rules you decided to start with.
And here's the kicker. When they rejected Euclid's parallel postulate, they didn't find just a bunch of logical chaos. Not at all. They discovered these strange, beautiful, and perfectly consistent new universes of space.
So let's take a look at the first of these strange new worlds, hyperbolic geometry. This is the universe you get when you assume that, multiple parallel lines can pass through a single point. Now to picture this, imagine a surface that curves away from itself at every single point. Kind of like a saddle, or maybe even better, a Pringles potato chip. That's the kind of bizarre, curvy space we're talking about here.
And in this world, the rules are totally different. The angles of a triangle, they always add up to less than 180 degrees. Now, I know it's hard to picture an entire universe like this, but we can actually map it out using these clever models, like something called the Poincare disk, which basically shows an entire infinite hyperbolic plane, all crammed into a finite little circle. It's wild.
Okay, so let's just break it down. We can see how these worlds differ at a really fundamental level. In Euclid's flat space, you get exactly one parallel line. Simple. In hyperbolic space, that saddle-shaped world, you get way more than one. Infinitely many, in fact. And then there's elliptic geometry. This is where space curves back on itself, like a sphere. Think about a globe. Any two straight lines of longitude, they look parallel at the equator, right? But they all eventually meet up at the poles. So in that world, there are no parallel lines at all.
So you've got this sudden explosion of different but equally valid geometries. And that led mathematicians to start searching for something deeper, a more fundamental structure. They started asking, is there some kind of master framework, some geometry that could contain all of these different worlds?
And it turns out the answer was yes. It was found in something called projective geometry. Funnily enough, it actually grew out of Renaissance artists trying to figure out how to realistically draw 3D scenes on a 2D canvas. Its core idea is that parallel lines do meet. They just meet at a point at infinity. Just like how train tracks seem to converge way off on the horizon. And this framework is so fundamental that Euclidean, hyperbolic, and elliptic geometries all pop out as special cases within it. All you have to do is change how you define distance. Okay, but for decades, these new geometries were seen as just beautiful mathematical curiosities. They were these elegant, logical games, for sure, but everyone thought they had absolutely no connection to the real physical world. Well, that was about to change, dramatically.
Let's go to the year 1905. There's a young patent clerk working in Switzerland. His name is Albert Einstein, and he publishes his special theory of relativity. And in doing so, he's about to connect all of this strange abstract math directly to the very fabric of our universe.
This was the stunning vindication. I mean, just imagine. Suddenly, that impossible geometry from Bolyai and Lobachevsky, it wasn't some abstract fantasy anymore. It was the precise mathematical language needed to describe the geometry of velocity in our own universe. It was real.
So, this whole journey, from Euclid's simple flat plane all the way to Einstein's curved spacetime, it just goes to show you how challenging a single long-held assumption can trigger a complete revolution, not just in science, but in philosophy too.
And that leaves us with a pretty powerful final thought, right? That the greatest breakthroughs might not come from finding new answers, but from having the courage to question the answers we think we already know. It really makes you wonder, what parallel postulate are we all just accepting as true today, just waiting for someone brave enough to come along and challenge it?